Good morning everyone. I am Amritpal Singh Nafaria from India. Today I am here to present my research work on modification of Newton's second law of motion. So here we begin with the background. According to the history, Aristotle was the first person who originated the formula of force. In observing objects around him, Aristotle noticed that large force resulted in large velocity, small force resulted in small velocity. However, in some cases, force resulted in no velocity. Here Aristotle added the concept of resistance. Here 1, 2, 3, 4 are the references given at the end of this presentation. Right? After Aristotle, John Philoponus suggested that Aristotle's relationship be modified as applied force is determined by the increase in velocity taken as a sum to the resistance. After Philoponus, John Buridan also modified Aristotle's relationship by replacing resistance with the weight. Far from these researchers, Newton saw things in vacuum. He didn't add the concept of resistance. According to Newton, force is equal to mass into acceleration. As per our study, this is the equation of net force, not applied force. There is a big difference between net force and applied force. We have explained it in next slide. Applied force vertically. Let a person accelerate 10 kg mass in the upward direction at the rate of 3 meter per second square. It seems the boy applied 30 Newton force, but it is actually not, because 30 Newton is a net force. So we not applied force. So to understand the concept of applied force, we have case 2. According to case 2, if the same boy holds same mass in the air on earth, then boy has to apply 98 Newton force just to hold it. So according to the concept, applied force equals to applied force till object is stationary, that is 98 Newton, plus net force, that is 30 Newton. So to accelerate 10 kg mass in the upward direction at the rate of 3 meter per second square, then we have to apply 128 Newton force, right? Applied force horizontally. Let a person apply force on a body of weight 50 Newton. Let the body stay stationary. So in that case, force by the push is equal to static friction, because net force becomes equal 0, right? So we have a formula of static friction. F is static friction, nu s is coefficient of static friction, and Fn is normal force. Let the coefficient of static friction between the body and the floor is 0.3. Then static friction would be equals to 15 Newton. Here we observe that we cannot calculate force less of a static friction. That means if the person apply 5 Newton force onto the body, then we cannot calculate it. In such type of cases, we just say force by the push is equal to static friction. This is not right. If the person apply 5 Newton force, then we have to calculate 5 Newton on a dot. Alright. Here is another case. Let two elephants pull a wooden log in opposite direction with an equal force. Here net force is 0, but that doesn't mean applied force is 0. There is a difference between net force and applied force, right? According to the equation, applied force is 200 Newton, right? Net force is 0, but applied force is 200 Newton, right? After uh, observing all these cases, we conclude that when a body stays stationary, even after applying force, then there would have been some resistance behind it. So by adding the concept of resistance to the net force, we have introduced the equation of applied force, right? Where F is applied force, R is the effect of resistance, and MA is net force, right? So let's calculate applied force by using this equation. To measure applied force to the body, we hang a weighing scale on the box and then applied force on it as shown in the figure, right? There we found that when force was applied to the box with the hand, the box moved when applied force exceeded 0.566 Newton. After then more than double of this force was applied, there instead of getting double, the value of R remained nearly 0.566 Newton, whereas the acceleration increased directly proportional to the applied force after it started from rest. There we observed that till the object was stationary, the R increased real quick, but when the body got motion, with the increase in applied force, only acceleration increased, whereas the R remained near about 0.566 Newton. Applied force horizontally when acceleration is 0. Now let us assume that the acceleration of a body is 0, and when the acceleration is 0, the equation becomes F is equal to R. To check the validation of equation, we hang a weighing scale on the wall and applied force on it. As shown in the figure, it is observed that when some force is applied with the hand by push, it applied horizontal force from the push equals to 4.4 Newton. When we apply some more force, then it equals to 13.1 Newton. When we apply even more force, then it equals to 21.3 Newton force. All these practical observations conclude that with the increase in applied force, the weighing scale reading increases with the same rate. Friction resistance. To calculate friction, the box was placed on 3 different surfaces in terms of friction, right? As we know, friction is the only resistance that was in motion, so we calculated the amount of applied force till the body stays stationary. So in first case, when we applied force, we noticed that the box moved when force exceeded 0.482 Newton force, right? In second case, we noticed that the box moved when the force exceeded 0.601 Newton. And in third case, we observed that the box moved when the force exceeded 0.566 Newton, right? All these practical observations conclude that with the increase in friction force, the applied force is calculated by the weighing scale also increases with the same rate. Air resistance. To calculate air resistance, we place the given box on the floor and created the effect of air resistance by using air blower, right? Here green object is a air blower, right? In first case, we applied force on a box, and we noticed that the box moved when the applied force exceeded 0.503 Newton. So in that way, we calculated friction between the surface and the box, right? In second case, we blow the air blower behind the box at low speed. Here we observed that the box moved when force exceeded 0.583 Newton, right? Here we know that the friction between the surface is 0.503 Newton. So by subtracting friction to the applied force, we get air resistance equal to 0.080 Newton in that case. In last case, we blow the air blower at high speed, right? Here we observe that the box moved when force exceeded 0.626 Newton. As we know, friction is 0.503 Newton. So by subtracting friction to the applied force, we get air resistance, that is 0.123 Newton, right? These practical observations conclude that with the increase in air resistance, the applied force is also increases, right? Applied force when body moves with constant velocity. In vacuum, a body can move in a straight line forever with a constant velocity without supplying any force to it. But on Earth, some force is needed to overcome resistances and move a body at constant velocity. On Earth, if resistance are constant, then we have to keep R constant to maintain constant velocity. That means if R is constant, then velocity will be constant. The value of R will change only when either applied force or the effect of resistance change. Hence, it concludes that when force is applied to a body, then to keep the velocity constant, we will have to keep R equals to resistances, right? Here are the references of the background, right? Here is my contact detail. I would seek your valuable suggestion, review, question. If you have any, then you can mail me or you can contact me, right? Thank you so much